Ever wondered why space is completely silent? First things first, we need to understand how sound works here on Earth. Sound is essentially a wave of energy that travels through a solid, a liquid, or a gas. When you speak, your vocal cords vibrate, compressing the air in your throat. This compressed energy travels outward, bumping into air molecules which then bump into their neighbors, and so on. A great analogy for this is a slinky toy. Push one end of a stretched slinky and a compression wave travels down its length. Sound moves through air in much the same way. The air molecules near your mouth bump into their neighbors, causing the sound wave to move quickly, about 760 miles per hour or 1,223 kilometers per hour. That's faster than a commercial jet. But what about space? Space is a vacuum, meaning it has almost no matter. The word vacuum actually comes from the Latin word for empty. Since sound needs atoms and molecules to travel, it simply can't move in space. There's nothing to carry the sound wave, so no sound can travel and no echo can occur either. If you were caught in space without a spacesuit, the lack of sound would be the least of your worries. The air in your lungs would expand due to the pressure difference, causing your lungs to rupture. You'd be unconscious in just 10 to 15 seconds due to lack of oxygen. Now let's talk about sound on other planets. Scientists have speculated on how human voices might sound on Venus and Mars. This is purely hypothetical, of course, since Mars is freezing cold with a thin, unbreathable atmosphere of carbon dioxide, and Venus is hot enough to melt lead. On Mars, your voice would sound tinny and hollow, like a piccolo. On Venus, it would be much deeper, like a booming bass guitar. This is because the thickness of the atmosphere affects the sound. The thin air on Mars creates a high-pitched sound, while the thick air on Venus creates a low-pitched one. The team that worked this out even simulated other solar system sounds, like a waterfall on Saturn's moon Titan. But did you know that space isn't entirely devoid of sound-like phenomena? Enter cosmic noise, also known as galactic radio noise, a fascinating physical phenomenon that originates from beyond our Earth's atmosphere. Now, cosmic noise isn't sound in the traditional sense. Instead, it's a form of electromagnetic radiation that can be detected using a radio receiver. This electronic device picks up radio waves and converts them into audible information, making the invisible universe come alive in a way we can perceive. Think of it as a cosmic symphony, inaudible to our ears but detectable through the right instruments. Cosmic noise shares characteristics with thermal noise, occurring at frequencies above about 15 megahertz. When highly directional antennas are pointed towards celestial bodies like the Sun or even the center of our Milky Way galaxy, they pick up this noise. Imagine pointing a telescope at the night sky, but instead of seeing stars, you're hearing the universe. One of the most intriguing sources of cosmic noise is quasars, extraordinarily dense objects billions of light years away. These powerhouses emit electromagnetic waves across the spectrum, including radio waves. The fall of a meteorite is another source. As it burns up from friction with Earth's atmosphere, it ionizes the surrounding gases, producing detectable radio waves. And then there's the cosmic microwave background radiation, or CMBR. This relic from the Big Bang pervades space almost uniformly, offering a glimpse into the universe's birth. The bandwidth of CMBR is wide, peaking in the microwave range, and it serves as a cosmic background hum that tells the story of our universe's origins. Now that we've delved into the concept of cosmic noise, let's journey back in time to meet the pioneers who first tuned into the universe's hidden symphony. Our story begins in August 1931 with Karl Jansky, an American physicist and radio engineer. While working at Bell Telephone Laboratories, Jansky built an antenna designed to receive radio waves at a frequency of 20.5 megahertz, which is roughly a wavelength of 14.6 meters. Over several months, he recorded signals and categorized them into 3 distinct types: nearby thunderstorms, distant thunderstorms, and a faint, steady hiss of an unknown origin. Intrigued, Jansky noticed that the maximum intensity of this mysterious hiss rose and fell once a day. Initially, he believed he was detecting radiation from the sun. However, as time passed, he observed that the brightest signal moved away from the sun and repeated every 23 hours and 56 minutes, a cycle corresponding to the rotation of the Milky Way. Jansky's groundbreaking work revealed that this radiation was coming from the Milky Way, specifically from its center. His discovery distinguished between the radio sky and the optical sky. the latter being what we see with our eyes, and the former revealing phenomena like daytime meteors, solar bursts, quasars, and even gravitational waves. Fast forward to 1963, when American physicist and radio astronomer Arno Penzias, along with his partner Robert Woodrow Wilson, made another monumental discovery. The duo was working on ultra-sensitive cryogenic microwave receivers at Bell Labs, originally intended for radio astronomy observations. In 1964, they created the Holmdel-Horn antenna, the most sensitive antenna receiver system of its time. To their amazement, they detected a persistent radio noise they couldn't explain. Seeking answers, Penzias contacted physicist Robert Dicker, who suggested that this noise could be the cosmic microwave background radiation, CMBR, predicted by cosmological theories, a radio remnant of the Big Bang. This discovery helped solidify the Big Bang theory of cosmology and earned Penzias and Wilson the Nobel Prize in Physics in 1978. NASA's work furthered these discoveries with the Absolute Radiometer for cosmology, astrophysics, and diffuse emission, ARCADE. This device observes the transition out of the cosmic dark ages as the first stars ignite in nuclear fusion, helping us understand how the universe began to resemble its current form. Carried by a scientific research balloon to an altitude of over 35 kilometers, 21 miles, ARCADE measures the tiny heating of the early universe by the first generation of stars and galaxies formed after the Big Bang. Now, let's explore another fascinating aspect of our cosmic symphony: the influence of solar flares and solar wind on cosmic noise. Cosmic noise refers to the background radio frequency radiation from galactic sources during geomagnetically quiet periods. This radiation maintains a constant intensity, painting a stable picture of the universe's radio sky. However, this serene backdrop can be disrupted by powerful forces emanating from our very own sun. Solar flares are sudden, explosive releases of stored magnetic energy in the sun's atmosphere. These flares cause a sudden brightening of the photosphere and can last from a few minutes to several hours. When these solar flares occur, they unleash particles and electromagnetic emissions that travel through space and reach Earth's atmosphere. This influx of solar energy increases the ionization levels in our ionosphere, leading to the absorption of cosmic radio noise as it passes through. Essentially, the sun's temper tantrums can momentarily mute the cosmic symphony we strive to hear, but that's not all. The sun also emits a continuous stream of particles known as the solar wind. Comprising protons, electrons, and nuclei of heavier elements, these particles are accelerated by the high temperatures of the solar corona, reaching velocities that allow them to escape the sun's gravitational pull. When this solar wind collides with Earth's magnetic field, it can cause sudden bursts of cosmic noise absorption in our ionosphere. These bursts are only detectable if the geomagnetic field perturbation caused by the solar wind shock is significant enough. So while Jansky, Penzias, and Wilson tuned into the steady hum of the cosmos, our sun occasionally adds its own dramatic notes to the symphony. These solar events remind us of the dynamic and ever-changing nature of the universe we inhabit.